In 2015, a groundbreaking scientific discovery was made. For the first time ever, we had directly observed gravitational waves, ripples in the fabric of space-time itself, emanating from the violent merger of two black holes located over 1 billion light years away. To date, a total of 50 gravitational wave detections have been recorded, mostly originating from binary black holes. But by analyzing a gravitational wave signal, we can actually extract a lot of the details about the binary that produces the signal, such as how far away it is or what the individual masses are. But what I am particularly interested in are their spins, that is, how fast the black holes are rotating on their own axes, and in what direction that motion is oriented. Now, broadly speaking, binary black holes can form in one of two ways. In the first scenario, we start with a binary system of two very massive stars. So massive that when the stars die, they collapse to form black holes, producing a black hole binary. In this case, we expect the spins to be nearly aligned with the orbit, as shown in the diagram on the left. However, if instead two black holes form separately from each other and then came together to form a binary following a close encounter, then we expect the spins to be randomly oriented, as shown in the diagram on the right. Furthermore, this misalignment between the spins and the orbit can actually cause the orbital plane to wobble or precess. The effect that the spins have on their binary's gravitational wave emissions can therefore provide clues as to how the binary originally formed. By identifying whether a merging binary has aligned or misaligned spins, we can begin to make statements about how likely it is that the binary formed from one mechanism versus another. But extracting the signatures of spinness from misalignment is quite challenging with the current generation of gravitational wave detectors. There's a lot of noise that we have to contend with, and this noise can often mask these subtle spin features. However, a series of upgrades to these detectors are in the works, and they promise to greatly reduce this noise. This has presented us with an opportunity to examine how well these upgraded detectors should be able to measure misaligned spins. The way I'm going about doing this is by generating hundreds of simulated gravitational wave signals corresponding to different spin orientations. I then embed these signals into artificial detector noise, taking these upgraded sensitivities into account, and then see how well we can recover the spins. What I have found so far is very promising and shows that these upgraded detectors should be able to measure the spins to higher precision than anything we've seen thus far with the current generation of gravitational wave detectors. There is a lot of exciting science waiting to be done with gravitational waves in the near future. So remember to stay tuned, and thank you very much.